This is going to be an example of computing an integral over a curve C of f dot dr. And we can look at it directly as a computation as f dot dr, but what we're also going to do is look at this as an example of applying the fundamental theorem of line integrals. So let's start taking a look at this. We've got a particular field here where P is given as 2x ln of y, Q is given as x squared over y plus z squared, and R is given as 2yz. Our curve is parametrized by the vector t squared, t and t, and we're going to go from 1 to e on that time. So let's just look at this as a standard line integral. So we got our integral over the curve C of f of r of t. So again, I've got to take x, y, and z to be their parametric definitions, and we would end up with an f that then looks like 2x, but x is t squared, so 2t squared ln of y, but y is t, so the ln of t. And we're going to go ahead and do the next component here, so x squared, so that means t to the fourth, over y, which is t, so that'll reduce down to t cubed, plus z squared, again z is equal to t, so that's t squared. And for the r, we get 2yz, so that's 2t squared, since y and z are both t. And I'll just go ahead and make this t to the fourth over t a t cubed now. And we would go ahead and dot that with r prime of t dt, remembering that dr is equal to r prime of t dt. We go ahead and find r prime of t, which will come pretty quickly. That's just going to be 2t 1 and 1 dt, and we would plug that in. So 2t 1 1 and a dt. At that point, you just go ahead and find that dot product. We're going to go from our integral 1 to e over our curve C. Our dot product is going to look like 4t cubed ln of t plus t cubed plus t squared plus 2t squared dt. So aside from this piece involving the natural log, the rest of this integrates pretty easily. And we could do that through a variety of methods that we have, probably just at this point plugging it in after simplification to some sort of computer algebra system, and we would get a solution from it. So directly computing this one, not all that bad. But again, we also want to use this as an example of the fundamental theorem of line integrals. And when we do that, we have to make an assumption that we have the potential function with us. Of course, at this point in our lessons, we haven't explored how to find that potential function. So let's just say that we're given that. The potential function f of x, y, z is going to be equal to x squared ln y plus yz squared. So if we have that this is the potential, for our vector field, then by the fundamental theorem of line integrals, we simply have to evaluate that at the end and at the beginning, much like any other integral. So really just applying it as if we were interpreting this potential function as the antiderivative of the field itself. We go ahead and apply it in that manner. So we have our integral then over C of f dot dr is just going to be equal to the potential function f of r at the end point, which is e, minus f of r at the initial point, which is at t equals 1. So then we go ahead and just set it up and solve it that way. We don't actually have to anti-differentiate because in a lot of ways, again, this potential function represents the antiderivative in a way of the vector field. So let's find f of r of t first. And again, that's just using that parametric definition for our curve to substitute in for x, y, and z. So remember that we had x equals t squared, y equals t, and z equals t, and we'll use those. So let's go ahead and do that now. So f of r of t is going to be equal to t to the fourth ln of t plus y times z squared. So that's going to end up being t cubed. And then it's just evaluating at the end minus the beginning. So f of r of e minus f of r of 1 is going to be equal to e to the fourth ln of e, which is 1, plus e cubed minus the value at 1, which is going to be the ln of 1 times 1. The ln of 1 is 0, so we end up with 0 plus 1 cubed, which is 1, and there you have it. So it looks like this is just going to be equal to e to the fourth plus e cubed minus 1. And again, this is really just a way to go through and see how we apply the fundamental theorem of line integrals. Obviously, in this case, some of the heavy lifting was done because we were given that potential function instead of having to find it. In later lessons, we'll look at how to find that potential function. And in the case of a more challenging integral here up above, we might be much better off if we've got that potential function to just use it. Or maybe we're working with a particular case where we already know the potential function, and then we can find various integrals. Say we're computing work over a vector field or something like that, using the potential function directly, as opposed to finding an antiderivative every time.